Okay, so in this video, let's talk about the Huckel rule. So using this rule, we can determine whether an particular compound is an aromatic or is it a anti-aromatic compound, right? I hope you have watched our previous video. We have talked about the electrocyclic reactions, and the important thing I want to notice here is that you need to have an idea about the phase inversions. We have talked about the phase inversions in our previous video, so I will put the link here. So if you have no idea about it, you can click through this link and go to that specific video and watch it. It's a very short video, so you will have a quick overview, very quick introduction about this phase inversions, right? Now let's see how we can apply this Huckel rule on particular compounds. So we can, yeah, so we can determine whether the compound is aromatic or anti-aromatic. The first thing is you need to draw the particular structure, right? So let's take an example, right? The first thing what you have to look at when you are determining this Huckel rule is that your compound must be cyclic, right? Your compound, so as an example, it should be like this. Your compound should be in cyclic array. Here I am representing the p orbitals. Now you can see that our compound is cyclic, right? Our compound is cyclic. So that's the first thing you need to see. Like if a particular compound is not cyclic, that you can't apply the Huckel rule. And the other thing is the phase inversions. Now let's say you have two bonds, right? Here like this and this. These are two bonds. Let's assume it, right? Let's assume it. Or let's go for three bonds maybe. Yeah, let's go for three bonds because it's more similar structure, which is benzene. Okay, now what we can do is we can put positive and negative positions for each orbitals, right? So here we can position this side of this orbital as positive and this side as negative. You can put any any signs, right? You can either put positive here or negative. It's completely up to you. And here you can put positive and negative, positive, negative, positive, negative, positive, negative, positive, and negative. Now what we are going to do is we are going to see the phase inversions, right? So look at this bond. You have to see the bonds and see whether the interaction between these two orbitals are on same signs or it's on the opposite. So as you can see here, this is positive and this is positive, so this is on the same signs, right? This is on the same side, so this would not be a phase inversion. There are no interaction between this orbital and this orbital, but there's an interaction between this orbital and this orbital, but the interaction is on the same side, so it is not an inversion, right? So if there's a particular bond, let's say it's like this, so our this orbital is interacting with this orbital like this, so this positive side is going to interact with this negative side. As you can see, the signs are opposite, so if that's the case, there is a phase inversion, right? That's called a phase inversion. Now in this case, for our case, there are no phase inversion up to now, because all the interaction between the orbitals are on the same sides. This is positive, this is positive. Interactions are on the same side. Here the same thing. Interactions are on the same side. So you can see our compound has zero phase inversions, right? Our compound has zero phase inversions. Now let's take another example, shall we? Let's take the compound like this. Now here we have the compound. As you can see, it's a cyclic compound, so we can apply the Huckel rule. Now we are drawing the orbitals. So let's draw the bonds like this. And now, as I have told you that you can put the positive and negative signs whenever you can, right? Like on whether you can put positive here or negative here, it's up to you. Now I will put positive here, and so this become negative, and I will put negative here, and so this becomes positive, and I will put positive here, and this become negative, positive, negative, positive, negative, positive, negative. So I will also change the bond order. Like, let's take another bond like this. Okay, here we have another bond like this. Okay, now these are the two interactions we have. Now let's see. Here we have two interactions, so let's see whether the interactions are on the same signs or the opposite. So if you look at this interaction, it's positive and negative, so it's not on the same sign, so there's a one phase inversion. So here you can see another phase inversion occurred. This is a negative one, this is a positive one. So these two orbitals interacting with each other on opposite sides. So this is also a phase inversion. So in total we have two phase inversions. Now the thing is, I have told you that we can put these positive and negative signs wherever we can, right? So if you take a particular orbital, you can put the positive sign in here, so the negative become here. Or you can put the negative here and positive becomes the other one. So if you change these sides, right? If you change these sides, look at this. If you change this side, I'm going to change this positive side. I'm going to make this one positive and this one negative. Now look at it. Now there are no phase inversions, right? This become positive, this become positive. So there's no phase inversions. There are no phase inversions. So phase inversions become 0. So always remember, if you have phase inversions a even number, right? If you have a phase inversions of even number, you can always reduce it to the 0, which means you don't have phase inversions. But if you have phase inversions an odd number, in that case you can't make it to the 0. So there are phase inversions. Now based on the situation, right, based on our compounds, we have two situations, which is we have no phase inversions, and the other case we have phase inversions. Most of the time, if you have even number of phase inversion, right, if you have, not most of the time, every time, right, definitely if you have even number of phase inversion, you can reduce it to the 0. But if you have odd number, you can't make it to the 0, so there will be a phase inversion left. Now if your system, right, so if you this system, if you can manage to reduce it to the 0 phase inversions, which means you have total of even number of phase inversions, we call this situation as a Huckel system. And in this case, right, in this case you can see there is a phase inversion, right, there is a phase inversion because you have an odd number of phase inversion totally. If you reduce it up to the lowest amount, you can't make it 0, you will take at least 0, at least 1, right, sorry, not 0. So you can't make it 0, you can't make the phase inversion 0 in this case. So if you manage to find a particular case, which means it's not an Huckel system, we call it as anti-Huckel system, right, anti-Huckel system. And the final step, right, final step what we can do is, we have to consider the pi electrons, which means 4n plus 2 rule or 4n rule. Now, if you look at the Huckel system, right? If you look at the Huckel system, if your number of pi electrons, accept the 4n plus 2 rule, which means the compound is aromatic. If your Huckel system follows the 4n rule, which is your compound is non-aromatic. Let's do an example, right? So in this case, you can see our phase inversions are 0, which means it's an Huckel system. So this is an Huckel system. So now what's the next step? You need to see whether our pi electrons satisfy this rule or this rule. So let's calculate our pi electrons. So here you have 2, 2 and 2. Total is 6, right? Total is 6. So which means it follows this rule, right? 4n plus 2. 4 times 1 plus 2. So this particular structure follows the 4n plus 2 rule, which means here it's an aromatic. Now if you look at this structure, right, first thing what you need to do is you need to see whether it's a cyclic or not. So as you can see, it's a cyclic one. And the next step, you need to see whether there are phase inversions. So you will see there are 2 phase inversions, which means it's an even number. So you can change these signs up and down and make it up to 0. So there are no phase inversions, or we can call this as Huckel system. Now the next step is you need to see whether your pi electron satisfy the 4n plus 2 rule or 4n rule. There are 2 pi bonds, which means there are 4 pi electrons. There are 4 pi electrons, which means it doesn't satisfy 4n plus 2 rule, it only satisfies the 4n rule. So which means according to this summary, your compound is non-aromatic. Your compound is non-aromatic. In this case, your compound is non-aromatic. Now, if you go towards the anti-Huckel system, right, which means you have phase inversions now. If you have phase inversions, then this thing changes. Now, the rules are the same, right? We have the 2 rules, 4n plus 2 and 4n. But the overall decision is changing. If your compound is anti-Huckel, right? If your compound is anti-Huckel, which means your compound has phase inversion, you can't make it to 0, then your pi electron satisfy the 4n plus 2 rules, then it's non-aromatic. If your pi electron satisfy the 4n, then it's aromatic. Okay, so you need to be very careful about it. First thing you have to do about any structure is you need to see whether it's cyclic or not. If it's cyclic, then you can proceed for the Huckel rule. If it's cyclic, you need to see whether there are any phase inversions or not, right? So you need to calculate how many phase inversions are there. If it's even, right? If it's the even number, the phase inversions are even, which means you are on the Huckel path. Your system is Huckel. Here, if your phase inversions are 0 or even number, then your system is a Huckel system. At that case, you need to calculate the pi electrons and see whether it satisfies the 4n plus 2 rule. If it satisfies the 4n plus rule, then it's aromatic, or else it's non-aromatic. Now, in the case where your cyclic compounds has phase inversions, it's odd number, right? You can't make it to 0, so it's an odd number. So it's an anti-Huckel system. Now in the anti-Huckel system, you need to calculate the pi electrons and see whether it satisfies the 4n plus 2 rule. Now if it satisfies the 4n plus 2 rule, then it's non-aromatic. The opposite of here, right? It's opposite of here. If it satisfies the 4n rule, then it's aromatic. I hope you get the idea, right? So this is all about the Huckel rule. Now in our next video, we will talk about the transition state aromaticity and also some phasialities. it will be some lengthy video in our next video. I hope you are okay up to now. If you have any questions, please feel free to comment below. I will try my best to answer your questions. So we will meet in the next video.